In automatic transmissions, the torque converter is the equivalent of the clutch in manual gearboxes. This component is capable of transmitting engine torque to the automatic transmission using only transmission fluid. In addition, when conditions require it, the torque converter can also multiply torque. Now let's see how it works. To transmit torque through fluid, the converter uses two components: the impeller and the turbine. Both are bladed wheels, although with opposite functions. Notice that the impeller rotates together with the engine, while the turbine rotates together with the output shaft. This animation shows how the engine drives the impeller, but the turbine is not affected by this motion. The situation changes when we fill the inside of the converter with transmission fluid. When the engine is running, the impeller accelerates the fluid by centrifugal effect, causing the fluid to leave the impeller with kinetic energy. The fluid strikes the turbine and causes it to rotate. The impact of the fluid on the turbine generates torque on the output shaft. Since the turbine is not mechanically connected to the impeller, its rotational speed depends exclusively on the energy it receives from the fluid. When the turbine rotates slower than the impeller, there is a speed difference between both components. This difference is called slip. Slip is a normal condition of the converter and is a direct consequence of its hydraulic coupling. Thanks to it, the engine can keep running even when the transmission is stationary, allowing the vehicle to remain still without shutting off the engine. And remember, you can explore the operation of this and many other automotive engineering components yourself at lagon3d.com. Now let's continue. When the vehicle is stationary, much more torque is required to overcome the initial inertia. To address this, the torque converter uses an additional component called the starter, located between the impeller and the turbine. The stator is connected to a stationary shaft through a one-way clutch. This clutch allows the stator to rotate freely in the same direction as the impeller and the turbine. But it locks if the fluid tries to rotate it in the opposite direction. Now you will see why this is essential. When the vehicle is moving at low speed, the turbine rotates much slower than the impeller. Under this condition, the fluid returning from the turbine does so in a direction opposite to the impeller's rotation. This flow attempts to rotate the stator in the opposite direction, but the stator locks. When it locks, the fluid is forced to change direction as it passes through the stator blades. This change in flow direction causes the fluid to return to the impeller in the same direction as its rotation. The result is an increase in the torque transmitted to the turbine. As the vehicle accelerates, the speed difference between the impeller and the turbine begins to decrease. The path of the fluid returning from the turbine gradually aligns with the direction of the impeller's rotation. At this point, the starter no longer opposes the flow. Since there is no force trying to rotate it in the opposite direction, the one-way clutch releases, and the stator begins to rotate freely along with the rest of the components. From this point on, the torque multiplication effect gradually diminishes. However, even though it no longer multiplies torque, the stator still plays an important role. Its geometry continues to guide the returning fluid so that it reaches the impeller in a favourable direction. Now observe how everything works together. Most modern torque converters incorporate a lockup clutch. When engaged, the lockup clutch mechanically connects the turbine to the converter housing. Rotation is then transferred directly from the engine to the output shaft. This animation shows how it is connected to the turbine. By eliminating slip, this mechanism significantly improves the efficiency of the system. The transmission control unit decides when to apply or release the lockup clutch based on variables such as vehicle speed, engine load, engine speed, fluid temperature, and throttle position. With this, we conclude the operation of the torque converter.